most it could lose given wherever it's sitting. Oh, no, just the difference between it and it's the difference between the temperature of the object and the environment. So in this case, it starts out at 70, but the room's at 10. The difference there. The difference between 70 and 10. Went from 70 to 50. Yeah. Yeah. No, what the projects haven't really completed yet. The amount that it actually lost, it started at 70. That was the figure. So it actually lost just 20 degrees. That's the actual. Yeah, there you go. That says the fraction. If you're going with negative there, that would also be negative. Losses. Ah, okay. You round it off. Yep.
And is it right?
Yeah. Okay, run it first because I was expecting, since it's white three remaining, I was expecting more threes.
Oh, here, I got you.
So you got the 1, 2, 3. So it's gonna lose a third of its temperature every 3 hours. Or a third of what it was. So now we're at 50 degrees Celsius, it loses 10. So this is gonna lose 40.
Oh.
The right number.
Oh, I was.
If you don't turn the on, then, yes, then that's probably good enough. All right, looks like most people are at least getting the fraction part. So in this particular problem, the actual temperature, the actual amount that was lost, I go from 70 to 50. So that's, I lose 20 degrees Celsius. And then the change in temperature max, the most it could possibly lose is from 70 to 10. So it's negative 60 degrees Celsius, or it loses 60 degrees, or the change is negative 60. So we end up with a fraction of 1/3. That is pungent.
Got this marker for more than a decade.
Still holds. So now I'm at 50 degrees and trying to figure out how much I'm going to lose. So the amount that I actually will lose, well, the most I could possibly lose now is from 50 to 10. And that's going to be equal to 1/3. or 0.3 or 0.333 or however many you want to take that. Sorry, need fresh air here. And so the change in temperature is going to be 40 thirds, or you're using a calculator, 13.3 repeating. One of these black markers will be non-stinky, and I guess technically negative is the change. So I start at 50, I'm going to lose 13.3, and you end up with 36.6 repeating degrees Celsius.
Wait, what did it?
Where?
Yeah. 36.
Are you good with here?
Mm-hmm.
All right, that's the change. That's what. So if I'm starting at 50 and I'm going to lose 13.3 repeating, I just subtracted 50 minus this, and I should have gotten this.
How did you get 40?
It is so now that I'm here, the most I could possibly lose is 40 degrees because the room is still 10. So 50 minus 10 is 40. Ashlyn?
How did you get 36.6?
Are you good with where I got the 13.3?
Yeah.
All right, that's the amount that I'm gonna lose. So I start out at 50 and I lose that, so it's just 50 minus 13.3 repeating. And it should,
I got 36.7.
it depends on how many threes you take out.
Okay.
If I had 36.6 and you had 36.7, I probably would not notice, except on a,
And you would take off for that.
right, possibly. On a quiz or test, odds are way against my noticing. Is there a hand up back there? I'm gonna put another problem up. I'm not gonna have us solve it, but just as practice for you. So, object, initial temperature, 80 degrees Celsius. The room, the temperature, which we assume is constant, some R for room, is 25 degrees Celsius. In terms of the language used on a quiz or test, I could say I have a small object in a large room. And that should be the indication that the temperature of the room is not going to change appreciably. Let's see, so after 2 hours, the temperature of the object is 65 degrees Celsius. So after 4 hours, the temperature is, and I have 54.09 repeating degrees Celsius. So just something to check on your room.
Will you ever give us a question where it's not like the same increments of time?
In 110, no. $251, yes, definitely. $151, that's one if I'm feeling cool or not. Other questions before I erase the rest of this? All right, so we have this change in temperature, we have objects that are, will expand or cool off at a certain rate, all that's well and good. What we really haven't touched on too much, it has been mentioned, is change of state of matter. So first, let's get some vocab down. Woo! We got the big three: solid, liquid, and gas. So when we have a change in phase, what we're actually doing is changing the potential energy. So we have particles that are really close to each other for the solid, but then they get separated apart. At some point, it becomes liquid. They get separated enough that it'll become a gas. So we're changing the relative position of the objects, of the type of particles. So if we go from solid to liquid, what is that called?
Melting.
Yep. Liquid to solid. Liquid to gas.
Evaporation.
I think vaporizing is usually used more than evaporating there, but that I'm good with either. Gas to liquid.
Condensation.
What'd you say?
Condensation.
Yep. Solid to gas. Sublimating. And then gas to solid. Depositing. Depositioning. We'll go with deposition right now. What did I write down here? I did just, I didn't do the gerund forms, I just did the noun of deposition. Now, sublimating is not something that we see on a regular basis, at least not that we notice. It is typically, the example that I can at least sort of picture is if you got a pile of snow, and yes, some of it will melt, but some of it will not actually melt. If you took a pile of snow and you put it into a pan, or figured out what the mass is, put it into a pan, there's not enough liquid in the bottom to account for the amount of snow that you lose. Some of it will go straight into gas form. There was a YouTube video where someone took a blowtorch to snow, and there was not a whole lot of liquid. It didn't melt a whole lot, and this person was using this as evidence that snow is not what we think it is. It's some horrible chemical. And then in characteristic internet fashion, someone said, I believe you're mistaken, something to these words. It's called sublimating. Yeah. All right, so how much energy does it take to melt or freeze? Yes?
When does a gas become a solid?
I can't say that I can think of a specific sort of everyday life example of that. Yeah, I don't have a everyday, I mean, a lot of the stuff can happen in in labs where you have nice controlled pressure and temperature. But did someone have an example?
The formation of frost on a cold window pane, where the water vapor in the air directly freezes into ice crystals without first becoming liquid water.
There you go. I always assumed it condensed first before solidifying, but I was wrong. KB, did you have your hand up?
Oh, I was gonna say as well, I don't know if you ever had like someone use nitrogen to make ice cream. Would that count?
But you're freezing that. That's going from liquid to solid, I believe.
True, never mind.
Yeah, I don't think that counts, but
What snowflakes, like forming the cloud, still gas.
I was still thinking it was in the liquid phase first, but maybe. Hey, I was wrong about that. All right, so when you're doing the melting or the freezing, you're actually not changing temperature. All you're doing is you've got the particles, let's say this has got a solid particle, they're really close to each other, not moving around a whole lot, and you are separating them. So the temperature is not changing, so whatever energy is required is not going to, the temperature, there's no temperature change. If you remember that, if you're talking about going from a solid at one temperature to a solid at a different temperature, we had MC delta T, we did that last week. But here, the amount of energy that's required is, well, it's material specific, and it depends upon the mass. So it's basically like MC. Now, the symbols that I use depends upon the semester and my mood. Sometimes I'll use a capital L. So this would be vaporization and solidification. Why is my mind blanking on that? Oh no, just freezing. So sometimes I'll use a capital L, sometimes I'll use a C. So if you're looking at any of my old stuff, you'll see one or the other. This stands for latent heat. Of freezing. Down here, you'll have L sub V for the latent heat of vaporization. So based upon the name, you would think, okay, if I'm going from liquid to gas, this would make sense because I'm vaporizing. But if I'm going from gas to liquid, what number do I use? Well, the same number. It's just a matter of whether you're putting energy in or taking energy out. If I'm going from liquid to gas, I'm putting energy in. I'm getting them farther apart. If I'm going from gas to liquid, I'm taking energy out. Now, sorry, not freezing, fusion. Latent heat of fusion. Maybe freezing didn't quite sound great. But I was going to run with it. Latent heat of fusion. All right, let's give some examples here. The latent heat of fusion for water is 79.7 calories per gram, or 530,000 joules per kilogram, or, sorry, not 5, can't read my writing, 330, or 330 joules per kilogram, or 330 joules per gram. So typically you'll also see plus or minus, because it depends upon energy in plus energy out minus. Latent heat of vaporization for water, 597.3 calories per gram. 2.5 million joules per kilogram, or 2,500 joules per gram, plus or minus. So if I was taking, let's say I have ice and I want to boil it. I start out with, there we go. I have temperature and I have energy. It's supposed to be in there. I'll have a freezing point or melting point, whichever way you want to go, and then I have boiling right here. So the first thing I would need to do is I would need to put energy into it until it gets up to freezing. So this is just purely change the temperature of the solid form of whatever it happens to be. Then I have to put energy in order to melt it. And then I put energy in order to get up to boiling. Energy in order to turn it into a gas, and energy in order to get it up to whatever my final temperature is. So if I want to figure out my total energy, I have to figure out my energy to bring it up to change the temperature, to melt it, to change the temperature, to evaporate it or boil it, change the temperature.